Unit 3, Part 2. So we're explaining what it means for the sentential operator AND to be a truth functional sentential operator. So as a speaker of English, you know that the word AND, right, the sentential operator AND, that any sentence built with the operator AND is going to be true whenever, in all cases, right, whenever both component sentences are true. And you also know, right, that if one or both of the component sentences is true, then the resultant sentence, right, the compound sentence, is not true, right? If I say blank and blank, or if I say A and B is false, you know that A and B is false, because that's what and means, right? It means these two things are true. That's what's being expressed. That's what's being told, right? Knowing that, you'll be able to recognize as the true semantics, right? The conditions under which sentences are true. That's what semantics is about. The true truth table of P and Q, symbolized with a dot, is going to be true in the first row. So we've got P and Q are the two component sentences, or sentential variables for P and Q, and in these, since P and Q is since the conjunction is a two-place sentential operator, and there we have two variables, so we've got two variables, so there are going to be 4 rows because we have to exhaust all the possible combinations of truth values, right? So P can be true or false, Q can be true or false, right? And Q can be true or false when P is true, and Q can be true or false when P is false. So these 4 rows list exhaustively all the possible truth table combinations. True, 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 false, false, true, false, false. Okay? When P and Q are both true, P and Q is true, and in all other cases it's false, right? Here Q is false, so P and Q is false. Here P is false, so P and Q is false. And when they're both false, it's false, right? In each row, right, each row represents an infinite number of substitution instances, right? Each row of the base columns each row itself represents an infinite number of pairs of sentences, right? I'm sure if I challenge you, you could think of, right, here's a pair of sentences where one's true and the other one's false, where the first one's true and the second one's false. Here's a second example where the first sentence is true and the second one's false. Here's a different pair of sentences where the first one's true and the second one's false. But for all of them, right, when I'm asked to determine whether P and true is false, I don't need to know anything about the content of the sentences. All I need to know is the truth value of the sentences. Knowing that P is true and Q is false is sufficient for me to know that P and Q is false. Right? Same sort of. That's what it means to say and is truth functional. The truth value of P and Q is determined entirely by the truth value of the component sentences. Now I'll go and show you what it means to not be truth functional, for a sentential operator to not be truth functional. So let's start with one at the top here. P, right, the sentential operator not P. It's only one place, so there's only one sentence to plug in. There's only one blank to plug in a sentence, so not P, we've only got one column here, just P, right? It's different from and is a two-place sentential operator, so we need 2 variables, P and Q. So there we needed 4 rows to exhaust all the possible truth value combinations. Here we just need 2. P is either true or false. So what's not P, you all know the meaning of not. Well, different logics will dispute that this is the correct truth table, but forget about that. If P is true, what does not P mean? What is the truth value of not P? Whenever P is true, not P is false, right? And if P is false, then not P, or is not the case that P is going to be true. Very intuitive, right? How that goes. Right? So now, see that I can I will not be able to, right, that's the truth table, right? And it is only possible to construct a truth table because the operator is truth functional, right? There are an infinite number of sentences which are true, right? But all of them, every single one of those where the sentence or the sentence is true, are gathered in this first row. So long as the sentence is true, that's enough to determine that not P is false. Right? For the infinite number of sentences where P is false, for all of them, not P is true. Just given the truth value of the component sentence, I have the truth value of the compound built with this sentential operator. It is a truth functional sentential operator. Steve believes that P is not a truth functional sentential operator, and thus I will not be able to put a unique truth value in here, right? It is going to be the case that when P is true, it's going to be the case that sometimes when P is true, Steve believes that P is true, but there are going to be other cases where P is true, but Steve believes that P is false, okay? And that, when I show you that that's the case, by providing such examples, I will have shown you that the truth value of the compound, right, the truth value of Steve believes that P is not determined entirely by the truth value of the component sentence. That's what it means to not be a truth functional sentential operator, right? We will have to look to more than merely the truth value of the component sentences to determine whether Steve believes that P is true or false, right? So if I tell you P is true, I tell you, is Steve believes that P true? You have to tell me, I don't know yet. I don't have sufficient information. I need to know about the content of the sentence. And that is distinguished, that is different from how it is with truth functional sentential operators. If I give you the truth value of the component sentence, you do have enough information to tell me whether the compound sentence is true or false, right? You can construct a truth table. These ones we will not be able to construct a truth table. Steve believes that P after Q. Okay? So, let's go ahead and demonstrate it. What we need to do, and again, you will be asked to do this in the exam. You'll be given an operator and asked to prove that it is not truth functional. On page 47, gives you the crucial instructions on how to prove an operator is non-truth functional. So I don't think focus there, but where this passage where the star is here, right? Where it says, so it suggests that if we could come up with pairs of component sentences with identical truth values and show that the results of compounding them are different, that means building the sentence with the sentential operator, this would be a demonstration of non-truth functionality, since it would show that identical truth value input does not imply the same truth value output, and that the value of the compound is not a function solely of the truth value of the components. So, the catchphrase there is, and I stress every time, every class, that this will be on the exam, and this is what you have to do, and people still do very badly in general on this question, on the exam. The catchphrase is same input, different output, where I mean same input, so you need different sentences. Here, it's Steve believes that blank, it's one place sentential operator, so it's just one input sentence. It's going to be different for P after Q. It's going to be two input sentences. But for Steve believes that P, you need two cases, right? With the same truth value input, but a different truth value output. So you need two different sentences. They've got to be different because they're going to have to lead to different outcomes. But two sentences that, while different, have the same truth value. So that just means it just means two true sentences or two false sentences. That's also two sentences with the same truth value. But here we're going to have two true sentences and show that the first true sentence, the first true P, will lead to Steve believes that P being true, but the second true P will lead to Steve believes that P being false. Okay, so first one is 2 plus 2 equals 4. That's a true sentence. right? Input is, the truth value of the input is t. Now the output, Steve believes that p is true. Steve does believe that 2 plus 2 equals 4. Steve hasn't seen me today. Danny's wearing a blue shirt. Yeah, call it blue. Let's say that's true, right? Danny's wearing a blue shirt today. True input. Steve believes that Dan is wearing a blue shirt is false, right? So we've got true input going to true output here, true input going to false output there. I'll continue the next part.